All right, welcome. We're going to be talking about blending objects and files in Google Cloud Storage. My name is Jeff Terrace. I'm a senior staff software engineer at Google. I've been with Google Cloud Storage for 12, almost 13 years, where I'm a tech lead for GCS's serving front-end team. So I work on our customer-facing APIs, routing, and sort of the front-end serving business logic. Before coming to Google, I did a PhD at Princeton that focused on object storage. So sort of been in this space for a while. And with me,
I'm Shufan. I've been at Google for, I guess, about 10 years in the cloud databases and cloud storage areas. And I'm currently a tech lead for the GCS Serving Fabric team. And I've been particularly focused on performance over the past,
So for the talk, we're going to start with a little bit of background on object storage versus file storage and what we mean by that. It'll probably be a review for most of you here. And then we're going to dive into 5 features in Google Cloud Storage that enables customers to bring file workloads to object storage. So we have Cloud Storage Fuse, which is a Fuse file system that customers can mount buckets. We have managed folders, which is so that customers can set access control at the object prefix level. We have hierarchical namespace, which is like directory buckets, where you can actually have some directory semantics. We've brought gRPC to our APIs. So gRPC is Google's high performance remote procedure call. And we're going to talk about how that unlocks some features. And then finally, we'll wrap up with rapid storage, which is a new feature that we're launching right now, which is a zonal storage product. And we'll talk about how it enables some new features to unlock some file-like workloads. So what I mean by file storage, trying to compare file and object storage. When we talk about file, we talk about POSIX compatibility. We talk about having a directory hierarchy. Typically, we think of like single-digit milliseconds for HDD. We think of like sub-millisecond for SSD. We think of hundreds of megabytes per second on the local system, potentially higher on remote file systems, and it's typically vertically scalable. So if you have a single file server, even with scale-out file systems, we still think of you make your machine bigger, more memory, more disks. You attach more disks to it to get to scale. On the other hand, object storage, we think of a simplified CRUD-L operation interface. So that's create, retrieve, update, delete, list. Very simplified interface, a flat namespace, so you don't have directories. Typically, you have higher latency access time than local disks. So we think of like tens of milliseconds, and it's typically horizontally scalable. So you can scale out. Each object can be served separately. And so that's sort of the difference. And what we're trying to talk about here is the contention between file and object. So we have customers that bring unmodified applications written for traditional file system backends, either local file system or expecting remote file system, and they expect the same semantics and performance when they wrote the application and tested it on those file workloads. And so there's some things that typically go wrong here, right? So, random writes and appends are difficult to support in object storage. Reading while writing is typically not supported. So there's a lot of problems with bringing these unmodified applications. And so we're going to be talking about how we sort of bridge the gap here and make these workloads work better on Google Cloud Storage. The first topic I'll be talking about is our Cloud Storage Fuse. And so I'm sure many of you are familiar with Fuse, but it's a file system in user space. It's a Linux add-on where you can create a user space application that is a backend for your file operations. So Cloud Storage Fuse, it mounts a GCS bucket to the local file system. So you have a directory and it looks like a bucket. You have all your objects in it. And it adapts /delimited objects names. Again, objects are a flat namespace, but we sort of pretend that they're directories by taking slashes in the object names and simulating a directory hierarchy. And this also supports hierarchical namespace buckets and rapid storage, which we'll talk more about later, about how those features help Fuse to adapt to workloads. So there's a lot of semantic challenges, though, when you implement this, right? So I'll give an example. If I call stat in the file system, and I say stat foo, When you mount in implicit mode, which is kind of like the default mode, you might have to do 3 service calls to figure out how to service that stat. First, you check if there's an object name called foo, and if there is, then it's a file. Then, but if it doesn't exist, then you have to check if there's an object named foo/. Because again, we simulate directories with what we call these, placeholder or marker objects that have a trailing slash and have no contents in them. They're just empty files that make it look like a directory. If that doesn't exist, you still have to call list objects to find out if there are any objects that have a prefix of foo/. Because again, you may not have created that directory placeholder or marker. You might just have objects names that happen to start with foo/. So, you can imagine this can be slow, right? Each one of these can take tens of milliseconds, and so your experience on Fuse might not be the best. So, we also, when you mount in the default mode, objects are only readable after finalization. You can imagine you have a lot of file workloads where, as you're writing a file, you want to be able to read it back. But with object storage, as you're uploading, you can't read data back as you're uploading it until it's finalized, and then it becomes immutable. So the way we sort of did this is we have 2 write modes. We have direct streaming mode, where it reduces latency and disk usage by just, as you're writing a file, it's uploading it to the object storage as you're streaming bytes. But again, you can't do random write support because it's a sequential append-only write mode. And you can't read while you're writing. So the file doesn't show up in the file system until you finish and until you call file close. On the other hand, we have what we call the staged local temporary directory. And so the way this works is, as you're writing files, it stages it in a local directory on the file system. And only when you call file close does it actually upload and synchronize to the cloud storage service. So this allows for random writes because you can write anywhere in the local file system as you're writing, and you can read the file back while you're writing it. But the trade-off is that there's long latency for the upload after you close, right? If you write a 100 gigabyte file on the local disk, it's going to take a while when you call file close to actually go upload that to the cloud. And it uses more disk space. Some customers might not have enough temporary disk space or not want to use a temporary disk. And so we also do a lot of caching, right? Caching is the classic way that you can improve performance locally. So you can tune this cache behavior based on what semantics you want when you mount your bucket. But this trades off strong consistency for performance. So for example, we have 3 caches that I'll talk about here. The first one is a file cache, so it caches object data locally. You can get some strong consistency still depending on how you configure it. So you can still talk to the cloud to find out if the, if you store some metadata locally. In Google Cloud Storage, we have generation numbers and meta generation numbers, similar to S3's version numbers, where you can say, oh, well, if my local cache still has the exact same data, I can serve from there. But you can also configure the file cache to not even look at the cloud. So you only, it's a sort of a write-through cache, or you interrogate your cache first. But that means that if the data has been uploaded or changed on the cloud, you're no longer have strong consistency with object storage. We also have a stat cache, so we cache the object metadata, like size, timestamp, file type, content type. We also cache negative existence, so that a file doesn't exist is also in the stat cache. Again, that trades off strong consistency, where now you have sort of a local view on your file system that doesn't necessarily match the source of truth in the cloud. And we also have a list cache, where we can cache the list of files and directories to make it less expensive when you list directories. And later we'll talk about rapid storage and how that helps with some additional features in Fuse. The next topic I want to talk about is managed folders. So managed folders, we have customers who commonly want to manage permissions at a prefix level. So similar to file systems where you can set permissions on a directory level, they want to be able to assign permissions on the prefix. Now, there are alternative options for that, right? So, we often tell customers, well, why wouldn't you just create multiple buckets? Each bucket can have a separate IAM policy. That often doesn't work. Again, if they're bringing unmodified applications that expect to have one bucket with multiple prefixes that looks like a file system, or, there's lots of various reasons why that may not be possible for all customers. There's also in a bucket policy, you can set conditions. So you can have like a starts with condition. You can say, apply this permission rule only for objects that start with this prefix. The problem with that is it doesn't scale. So, if there are policy size limits, and so if you have, thousands or millions of prefixes, it doesn't scale that widely to have a single bucket policy. We also have per object legacy ACLs, so you can set permissions on an individual object basis. But that's really hard for customers to manage. They have to make sure that they apply the same permissions to every object that's underneath a prefix. Doesn't scale well, it's hard to manage, and so it's hard to reason about shared permissions at the prefix level. So the way managed folders works, you can think of it as an adjacent resource that has IAM policies. So you sort of set up your managed folder tree separately from your objects in your bucket, and a managed folder that has a name that matches object names will apply the permissions to those objects. So there are some challenges here to scale this, right? So one of the key scalability attributes of object stores is that you have a flat namespace. You can scale widely horizontally because each object is independent, except for bucket. But so for an example, if you're accessing an object name foo/bar/baz/x/y/z/file.txt, you may need to check all of these prefixes to see if there's a managed folder at that level. So now one object operation can fan out to multiple managed folders operations to find out if there's an IAM policy at that prefix. So we did add some constraints here, right? So you can have a maximum of 15 levels of nested depth with managed folders. We found that number is sufficient for the majority of customers. Very few people hit this limit. We also, we document that there's a delay in policy changes. So you can imagine that's, because of caching. So if I update an IAM policy on a prefix, it can take up to a minute for those permission changes to propagate down to object operations that are underneath that prefix. And we also, we can skip work if there are no managed folders. So basically the first time you create a managed folder, we mark a metadata field in the bucket that says, hey, there are managed folders in this bucket. So if there are no managed folders, we just completely skip this code path so that if you're not using managed folders, you're not hit by any performance problems that could arise with managed folders. And obviously, again, caching, as you're going to see that as a theme here, we do lots of caching. So I'm going to talk about one of the core caches that we use for managed folders in order to still maintain good performance. We have this two-level cache. What we do is we have a cache from the sort of leaf prefix to the depths within the path that have a managed folder. So you'll see the box on the left here, it's dir1, dir2, dir3, dir4 might map to a cache value of 1, 3. And what that means is it's zero-based, so that means that dir1 does not have a managed folder, dir2 does, dir3 does not, dir4 does, right? So it's telling you which of the prefixes in the path have a managed folder. And then we have a second level cache, which maps the actual managed folder names to their IAM policy data. And so the reason we do this, this two-level cache is what we see in practice is customers typically access a single prefix at high load at the same time. So you can imagine, I have a analytics workload that is writing output files to a prefix. All your writes come in at the same time. Similarly, the next stage in the pipeline reads all of the files at the same time, right? So you often get co-location of workloads for a single prefix, and by caching the full path, that first cache tells you where the managed folders are, then the second cache lets you get the data. So we find that this two-level cache works really well in practice to minimize the performance cost of implementing managed folders. The next topic I want to talk about is hierarchical namespace. I mentioned that objects have a flat namespace, but we've launched this feature called hierarchical namespace. It makes your bucket look more like a directory structure. So at bucket creation time, you can select to turn on hierarchical namespace. It organizes your objects into folders, just like a local file system structure. It has some backwards compatibility, so if you create an object with lots of slashes in it, it will implicitly create all of the intermediate folders along the path. And it enables new features, like you can atomically rename a folder, which applies to all of the objects underneath that folder, regardless of how many objects are in that folder. We require IAM-only access control, so you can't use legacy ACLs with this mode, but you can use managed folders, so you can apply IAM policies at the prefix level or folder level in these types of buckets. And I'm going to share a little bit about how we implement this in the back end. So this is a picture of, sort of a simplified picture of what our metadata storage looks like for the hierarchical namespace layout. So at the top level, we have a bucket shard table. So we're doing hash sharding. You can see the shard in the bottom left. It's the hash of their dir node ID, which I'll talk about in a sec, and the base name. We hash that to figure out what hash to look at the sort of root of our metadata table. And we do support dynamically sharding, right? So you can get better scale out operations by expanding the hash count or contracting it based on load. Underneath the bucket shard, we have directory metadata and dir node. So the idea is that each directory has a node ID, the dir node table. And then there's a directory metadata that has the bucket name, the directory path, and then it points to the dir node ID. Lastly, we have the object metadata table at the bottom, which has bucket names and an object name. This is the same table that we use in flat buckets. And so you can see we kind of overloaded the object name here to add additional information in the field. So the field is the bucket shard number followed by the dir node followed by the object name. So an object, the string that's in the object metadata table, the nested here, that's only the last part of the path. So the dir node is where it tells it what directory it's in. So by using this structure, you can go and rename just you can do one update in the directory metadata table to change a directory path, and all objects that are underneath it automatically get changed with their path to apply the new directory name. So that's for leaf nodes. We do have, so leaf nodes become like a very cheap atomic operation to rename a leaf directory. Interior folder names, they are atomic, but they're a little more complicated. So we have what we call a long-running operation where you sort of initiate an operation, then you can wait for it to complete. In practice, the latency is pretty good. What we do is we have this protocol where we sort of start at the top that you're renaming. We walk downwards in the tree and we start locking the directories so you can no longer modify them. Once all of the directories are locked downwards, we start renaming back upwards and unlocking as we go. And so the way this works is, you can't mutate the directory structure while it's locked, but we sort of minimize that locking time so that the availability is window of unavailability for writes is minimized. And by doing that, we can allow interior node renames with pretty good performance. This does have an implication on flat bucket object listings. So because of the hash sharding, you have to do sort of a merge sort, right? The object listings are sorted by object name. So you have to go and query, up to your shard factor in parallel and then merge them back together to form a sorted object listing. It does become slower, but the way we alleviate that, we tell customers to list directory by directory. So instead of doing flat, list all my objects in the bucket at once, you go directory by directory, and listing one directory is we can still have good performance. And again, we do have to traverse the directory hierarchy in order to serve object operations. So if you have a deep path, we have to go read all of the, potentially all the dir nodes or directory metadata in the path. But we heavily cache this to minimize cost, and we find that we're still able to maintain good performance for customer workloads. The next topic, I'm going to hand it off to Shufan, who's going to talk about gRPC.
So I think Jeff talked a lot about by imposing this sort of hierarchy, it opens up a bunch of opportunities for customers to perform a bunch of operations that were a little bit hard to do previously. I'm going to talk a bit more about a bunch of the changes that we've made that end up offering more file system-like semantics at the individual object level. So first off, we've recently introduced gRPC as a API to access GCS. gRPC, if you're not familiar, is open source, it's interoperable, and it's feature-rich. Namely, one of the interesting things with gRPC that's sort of new for us is it opens up the opportunity for bidirectional streaming with additional authentication options. And this bidirectional stream also gives us the ability to send traffic more directly to our backends. gRPC is a Google-developed technology. It relies on protocol buffers instead of JSON or XML, and it has meant that there's existing libraries and frameworks that enable this to work across many languages and platforms, but it is a little bit of a switch. So if you're sort of not familiar, we typically have XML as our sort of like S3 compat layer. We have our own JSON API, and then we have a gRPC API as well. There are some sort of differences, but I think the main thing again is with gRPC, this has opened up the opportunity for us to do more sort of stateful streams. I had mentioned that this allows us both from a authentication as well as from a direct connectivity point of view, some additional advantages. So within Google, when we want to serve HTTP API traffic, typically there is a fronting load balancer reverse proxy type service that we internally refer to as a CFE. And this sits between GCE VMs or outside internet traffic and GCS's storage front ends. This has to proxy traffic. It comes with some performance, both latency as well as throughput limitations. And then again, since we use HTTP, this is the normal TLS sort of authentication. With gRPC, we're able to cut out that CFE hop. So we still have load balancers in the mix to help direct traffic correctly, but more of this responsibility is moved to the client. And then there is a new authentication protocol called ALTS that Google has developed. The primary difference between TLS and ALTS is that it allows us to authenticate the client and the server. And so we can use this. I'll talk about this, some of the advantages that we're able to use this for later on. But at the same time, right, by moving the load balance, some of the load balancing machinery into the client, and with ALTS, we are able to then have the VM directly communicate with the specific cloud storage front end that the data may be on. And so yes, and then the other thing is by keeping the stream open, and by keeping the stream open. This allows us to do multiple operations within a single stream. This has advantages for both reads and writes. So for reading, a very common use case is that applications will want to read multiple disjoint ranges from a single object. And so the sort of like canonical example of this, I see some of you smiling, is like Parquet files where you have a footer which gives you a bunch of offsets, has a bunch of metadata, and then you'll want to likely seek into different portions of that object. And so like in the current world, with our existing HTTP APIs, these would require multiple HTTP range read requests. So in this example, right, you want to fetch multiple ranges from a bucket object, and each of those ends up being its own independent HTTP request. Each of those requests results in additional overhead, which eats away at performance. We'll have to do multiple authentication and authorization steps. All the things that Jeff was just talking about, where we have these metadata lookups in the loop, further slow down that request. And then finally, from a data read, we will have to then also make requests from our API front ends to the underlying storage servers, even if it might actually end up being the same underlying in Google Colossus file. So with bidirectional read object, we're able to smush all these into a single stream. So you're able to open a stream, and then you can issue multiple read ranges within that stream, and then those responses will stream back. One of the things you may notice here is that we don't necessarily return in exactly the same order, so you can queue up a bunch of range read requests before any response has been received. So if you don't have data dependencies in your I/O patterns, for example, it means you could queue up, say, those 3 reads in the middle, and then we'll just return them as fast as we are able to read that data back. And so since we are able to keep the stream open, as I mentioned, this means that the authentication and authorization gets performed once at the start, and we can amortize, the metadata lookup time as well. Since we just have to do that once, it remains cached, or it remains in memory for the duration of this stream, and we don't have to redo it. We don't have to worry about caching, all those things. You open this connection, and you're consistently reading from the same object version. And so this is great for Google because this reduces some of our serving costs, but more importantly, it reduces the latency of this type of workload. And we find that this is a very, very common I/O pattern, and so we're pretty excited about this. We're first going to be this is going to be first introduced on rapid storage, which I'll talk a little bit about more in terms of because that has made some changes in our I/O and storage formats, but this notion of being able to expose a nicer sort of read object API has been really helpful for accelerating those specific workloads. And then I had sort of mentioned at the beginning, I come from a database background. One thing I'm quite actually excited about is we've also introduced bidirectional write objects. A lot of applications need to be able to write data in sort of this streaming fashion. A very common case for databases would be transaction logs, where you want to be able to continuously write transactions as they're committed. And in the current form, we're forced to write within GCS. You normally would have to write object at a time. You have to pick how big you want those objects to be. The larger the object, the less operations you have to do, and the less latency overhead, and the less objects you're creating. But also, it means that the RPO, right, the amount of time that you have to go between flushing logs increases. There's sort of similar trade-offs you could imagine for many other use cases, like Kafka or like log-type pipelines. The other thing is that, what we have done here is you can continuously append to it. You can open an object and then continuously append to it. In this example diagram, you can see multiple write requests for 2 megabyte chunks are being sent out, and then periodically, as part of the protocol, you can say that you want confirmation that the write has been flushed, and then in which case it will return. In which case GCS will return confirmation. This allows on the client side, it means that you have when your writes are made durable. One nice thing and then as I was mentioning, one of the benefits here is by doing this, so one of the things by doing this is you don't, as Jeff was mentioning earlier on with fuse and writing, right? If you want to write very large objects, you have to be able to buffer the entire object in memory, or you have to use either MPU or resumable uploads, those protocols, in order to sort of chunk the request. Similarly here, clients can chunk and flush within a single stream. And again, by keeping this as a single write session, on the server side, we're able to then keep a bunch of the state necessary to continue to append to an object, and you don't have to pay that sort of initialization cost with each of these subsequent requests. We're also launching rapid storage as we do this. There's some changes that we're doing within GCS from a on-disk format perspective. As well as sort of the data placement that allows us to move more in the direction of offering both more file-like semantics and also more block system-like performance. So typically within GCS we have regional or multi-regional buckets. And so in Google, or similarly with like S3 as well, you'll think of a region as being something, say, like US Central 1. And then those regions are composed of multiple zones. So for example, US Central 1F would be a zone. With Rapid, you create a bucket that is homed in a specific zone. This means that you're able to co-locate your compute and your storage in the same zone, less network distance, higher performance, both from a throughput and latency point of view. And then I talked a lot about about some of these gRPC capabilities, right? With these stateful streams, with this additional routing, this enabled us to do more things with Rapid. We're also building on top of Colossus, which is Google's cluster-level distributed file system. And so here again, Colossus ends up being sort of closer to the zonal level. We're still able to maintain the same strongly consistent, durably replicated capabilities that customers are used to. Modulo, some hand-waving around. Like I think with zone versus region, there's going to be slightly different reliability characteristics. But again, this allows us to, once the stream has opened, to both perform subsequent range reads and appends significantly faster. This allows for very, very high QPS. We don't have to round trip through our metadata, like spanner databases. This allows for increased throughput because we're able to write directly to Colossus or read directly from Colossus without having to interpose metadata in between. And there's no limits on appends. There's no limits on append size. So, in that initial drawing, I had mentioned there's a load balancer and then direct connections with alts for authentication. One of the big changes we're making with Rapid Storage is this route lookup. We can fetch information about the bucket. Our SDKs extract the bucket name, and as part of the gRPC connection initialization, send that to a route lookup service, which then provides additional metadata, which allows us to more directly have the GC VM connect directly to backends that are able to serve the traffic. Normally, we are sending this to, say, a regional backend or a multi-regional backend. But in this case, we're able to send it directly to a zone very, very close to the specific location where the data is being stored. With sort of obvious advantages, both from a network locality point of view, as well as meaning that these tasks are going to be significantly hotter in terms of like having connections open to those storage servers. I mentioned the BiDi read object protocol. Another thing that we can do with Rapid is this notion of having a read handle. So when you open a read stream, you also get a handle back. This handle is time-bound and locked to a specific VM, but this allows clients to then open a handle and then use it to perform reconnects. So since the stream to the front end is this means that the stream to the front end is already open, and then under the hood we have a RDMA-like protocol between our API, the cloud storage front ends, and then Colossus underneath. So this reduces the overhead in terms of reading individual blocks from our underlying storage systems. This, in some ways, may be familiar from a object point of view with normal file system, where you can open an object, a bunch of the metadata is now sort of cached, and then subsequent reads within that open object or open file become faster. This is something that within Google we've internally used for a number of BigQuery and analytics workloads, and we find that this is really beneficial for performance. The other thing is we've added more stuff around writes. So we have to be very, very careful about fencing, and you don't want to have a case where multiple clients are appending to the same object. So if a client fails or crashes, a new writer can take over for appending. On our side, this requires having a sequence number that we acquire via spanner. So this is strongly consistent. And then we integrate that into the Colossus metadata to guarantee that the latest writer is the only one writing, and to be able to, if the sort of crashed VM was like closed due to a network partition or something, if it later shows up, we can then reject the request saying, sorry, you're not the latest writer. So this is a bunch of additional work that we've done to try and provide, again, sort of more file system type semantics. You can allow for exclusive writer capabilities. All right. I think I finished a little bit early.
How do you deal with current operations coming in through file semantics, gRPC, and object semantics? Can you repeat the question? Summarizing.
Yeah, so the question is, how do we deal with concurrent operations coming both from gRPC with file-like semantics versus objects coming in at the same time? So we sort of we try to maintain backwards compatibility with objects. So if you have like a rapid storage bucket, our serving front ends are sort of using the file system protocol under the hood. So like if you try to write to an object, we will do acquire a write handle and do the write fencing for you on our front ends. And because of that, it allows us to maintain the consistency that we have for just like if everyone was using the file protocol. Does that answer your question?
Do you support inserts like writes inside the middle of an object without having to rewrite the whole object? Because that's another issue that's sometimes encountered for updates.
Yeah, we don't allow that. It's currently append only. You can read while you're writing, and it's append only, but we don't allow random writes. Yeah.
We do allow compose as well, so you can compose multiple objects and inject into the middle that way, but it requires you to write those parts out initially.
Can you create a new object from parts of an existing object so you don't have to resend that?
It would have to be like separate object. Oh, sorry. So the question was like, are you able to compose from parts of an existing object? And no, they're on an object by object basis. I think a big part of I think the way that we I think it's the way that we split our world in here is there's a set of things that we're able to enforce via relying on spanner and maintaining consistency through like the consistent database, and then we have to maintain a set of invariants around the actual data storage as well.
Got it. So with the fuse file system, if I have a gigabyte object, I open that, I modify it, it's downloaded the whole object, made the change locally, and then uploaded it again.
Yeah, so the question is like if you, with Fuse, if you would download an entire object, you perform some modification on a portion of it, you do have to re-upload the entire object. And I think there's basically, we end up with a bunch of effectively sharp edges where we try and provide file system-like behavior with Fuse, but then in many cases where our backends just don't support something natively, that does mean you have to do sort of these hacky things that have like surprising performance implications.
And so many of these use cases are going to be primarily read-based and then write in a separate, you're creating new objects, you're paying. So you're going to get most of the use cases there anyway.
Right. I think, I think, I guess to repeat the question, to repeat your statement, yes. We often will see customers read a bunch of objects, do some AI training, and then write out a bunch of output files. And when we talk, we describe a bunch of these limitations around caching, like these sharp edges is, ideally you are writing to new objects if you want to enable certain kinds of caches, because otherwise there's that risk of inconsistency.
Yeah, so to repeat the question, is there if you mount so I mentioned implicit mode, you're asking about explicit mode. So yes, we do have an explicit mode in Fuse. If you mount a hierarchical namespace bucket, we have a whole new set of APIs for directories. So you can create, or for folders, you can create folder, you can delete folder, and so it will actually, instead of just creating objects and having it implicitly create the folders, it will do more explicit calls to the namespace. And then, sorry, what was your second question?
Implicit mode, directory, place on directory, how do you store that?
So the question is, in implicit mode, how do you store directories? Yeah, so we. Yeah, so I don't think we support A-time, but we do. I think Fuse will create directory placeholder objects, so it'll create objects with slashes in them. Like if you, in the file system, if you say create dir, it'll go and create a placeholder object to sort of simulate creating the directory. And we do have, there's an API at the bucket level where you can get, it's called get storage layout, which will tell you whether it's a flat or a directory bucket or hierarchical namespace bucket. And Fuse will use that to decide what mode, which APIs to use to support those operations. Sorry, can you?
How did you optimize the year goal to work well for SDC?
So the question is, how do we optimize gRPC to handle like high throughput? Yeah, so there can be issues with gRPC with throughput. I think, so we do also have two modes of gRPC. So we have, if you're outside of Google's network, either in your on-prem or if you're out of region on GCE, we use the same sort of cloud front ends and it goes over HTTP. And so that, it's using TCP, HTTP. Versus if you're in region on GCE in the same location as your bucket, we use the direct connectivity with the ALTS, which is a different protocol. I don't think we've struggled too much with throughput. I know that many of the languages do have zero copy buffers where you can get high performance. I think we've seen higher performance on gRPC versus like our JSON APIs. But maybe we can talk offline about sort of your negative experiences with it. Yeah. Questions? Yeah.
Talk about an RDMA-like thing from the front end. Is there more information on that?
I think it's public, but do you want to say a little bit about it?
RDMA-like.
So the question is, I had mentioned that there is an RDMA-like protocol between Google's underlying Colossus storage and our front ends. I am not sure we have publicly talked too much about it, unfortunately.
But but I think we can say, generically, it's a protocol that skips some of the network stack and some of the overhead when you're in the same data center as the underlying storage. Any other questions? Okay. Thank you.